Welcome. Today we will determine the domain and range of 5 functions involving absolute values. For each one, we will not just state the answer. We will actually work through the calculation and then sketch the graph to visualize it. Recall that the domain is the set of all input values, usually x values, for which the function is defined. And the range is the set of all possible output values, usually y values, that the function can present as the input varies over its domain. Let us begin. The yellow curve shows f of x equals the absolute value of x. Let's calculate. Absolute value of x is defined for every real number x. Since absolute value of x is always greater than or equal to 0, and equals 0 exactly when x equals 0, the smallest output is 0, with no upper limit. Therefore, the domain of yellow curve is all real numbers. So the range is the closed interval from 0 to positive infinity. The blue curve shows f of x equals the absolute value of x plus 2, since absolute value of x is defined everywhere, because absolute value of x is at least 0. Adding 2 makes the output at least 2. This shifts the whole graph up by 2 units. Therefore, the domain of blue curve is still all real numbers. So the range is the closed interval from 2 to positive infinity. The red curve shows f of x equals the absolute value of 2x. The expression 2x is defined for every real x. So the domain is still all real numbers. The absolute value of 2x is 0 only when x equals 0, and positive everywhere else. Multiplying the input by 2 squeezes the graph horizontally, but does not change the minimum value. Therefore, the domain of the red curve is still all real numbers. So the range is still the closed interval from 0 to positive infinity. The orange curve shows f of x equals the absolute value of 2x plus 4 minus 3. To find the vertex, we set the inside of the absolute value to 0. 2x plus 4 equals 0, which gives x equals negative 2. The absolute value term is never negative, so its smallest value is 0, which happens exactly at that vertex. Subtracting 3 shifts that minimum down to negative 3. Therefore, the domain of the orange curve is still all real numbers. So the range is the closed interval from negative 3 to positive infinity. The purple graph shows f of x equals x divided by the absolute value of x. Since we are dividing by absolute value of x, the denominator cannot be 0. So x equals 0 must be excluded. Now, for any positive x, absolute value of x equals x. So the ratio simplifies to 1. For any negative x, absolute value of x equals negative x. So the ratio simplifies to negative 1. Therefore, the domain of the purple graph is all real numbers except 0. So the range contains only the two discrete values, -1 and +1. In summary, looking at all 5 functions together, we see how algebraic shifts and transformations alter the graph and, with it, the range. Functions 1 through 4 are continuous and their domain is always all real numbers, because there is nothing inside an absolute value that can make them undefined. Their ranges are intervals determined only by the vertical position of their vertex. Function 5 is different. It has a variable in the denominator, which forces us to exclude a point from the domain, and it produces a step graph with a discrete range containing only 2 values. Now let's watch these functions connect to each other by building f of x equals absolute value of 2x plus 4 minus 3, one transformation at a time. Starting from the simplest curve, the absolute value of x. Step 1. We start with f of x equals absolute value of x. Its vertex, the sharp corner, sits at the origin, at the point 0, 0, because that is where the expression inside the absolute value is 0. Step 2. We replace x with 2x, giving absolute value of 2x. Setting 2x equal to 0 still gives x equals 0. So the vertex stays at the origin, but every point moves horizontally toward the y-axis. The graph becomes narrower. It is compressed horizontally by a factor of 2. Step 3. We replace 2x with 2x plus 4, giving absolute value of 2x plus 4. Setting 2x plus 4 equal to 0 gives x equals -2. So the vertex slides left, from the origin to the point -2, 0. This is a horizontal shift. Finally, we subtract 3 from the whole expression, giving absolute value of 2x plus 4 minus 3. This moves every point down by 3 units. So the vertex ends at -2, -3. That is exactly f4 of x, built up piece by piece from f1 of x. Thank you very much for your patience.